Alright guys, in this section we're going to be discussing related rates and how chain rule can be used to find the rates of change of two or more related variables that are changing with respect to time. So here time is going to be our independent variable. Alright, so we're going to follow a couple steps here, a few guidelines for solving related rate problems. These are just common suggestions that will help us set up our problems. Number one, identify all given quantities and quantities to be determined. Make a sketch and label the quantities. Okay, so in other words, identify the knowns and the unknowns. Number two, write an equation involving the variables whose rates of change are either given or are to be determined. Okay, so just like we did for the variables, you also want to do that for the rates of change of those variables. And then number three says, using chain rule, implicitly differentiate both sides of the equation with respect of time. So this is the part where chain rule is going to play a big role. It's going to be very important because all of the variables that you identified in step one are going to be functions of time, so that when you differentiate, you're going to think of them as functions of time. You have to apply chain rule to them. And then last but not least, we have, after completing step three, substitute into the resulting equation all the known values for the variables and their rates of change. So we're going to substitute everything that we know after we differentiate, not before. Then solve for the required rate of change, which is typically what we're going to be asked to find. Okay, so here we have an example. The radius r of a circle is increasing at a rate of 4 centimeters per minute. Find the rate of change of the area when r, the radius, is 37 centimeters. So we have a sketch here of a circle, radius r, and so we identify our quantities. We have, for one quantity is the radius here. We're going to call it r. And the other quantity is going to be area, right? And we're going to put those two quantities into an equation that we're familiar with here. And this is the area formula for a circle, equal to pi r squared. Once we have an equation that relates both of our, or all of our variables here, in this case a and r, we're going to differentiate implicitly with respect to time, with respect to t. And remember, think of a and r as functions of t, functions of time. So that when you take the derivative here, with respect to time, you get dA dt is equal to the derivative of everything on the right side here. Now pi is just a constant, so and r is a function of time. So then we're going to apply our rules of differentiation here. dA dt is equal to the derivative of pi r squared. We bring the 2 to the front, multiply times pi, that's just power rule, times radius times r, and chain rule says to multiply by the derivative of r with respect to t, dr dt. Okay, after we're done with the derivative, we're ready to substitute all our values that are given in the problem, and we want to find the rate of the area, rate of change for area here with respect to time, so that's dA dt. So that's equal to 2 pi. The radius is 37 centimeters here, and I'm going to put the units here so that you'll see exactly what we're going to get at the end. There's no ambiguity here. And then the rate of change of the radius here is given also by the problem, and that's 4 centimeters per minute. Right, putting this whole thing in the calculator, we get the dA dt is equal to 929.9 centimeters square per minute. This dA dt is the rate of change of area. Okay, here we have another example. Now instead of area, we're going to be looking at volume here. Instead of having a two-dimensional figure, we have a three-dimensional solid here. The radius r of a sphere is increasing at a rate of 3 inches per minute. So if radius is r, then the rate dr dt is going to be 3 inches per minute. That's how we represent it. So again, after we have our picture here, our sketch, we start labeling our knowns and our unknowns. And the first question is find the rates of change of the volume when r is equal to 9 inches and when r is equal to 36 inches. So 2 questions within that first part there. Now bring everything together here, all our variables in this volume formula, and the volume of a sphere is 4/3 times pi times the radius cubed. Once we have our equation here, we're ready to differentiate with respect to time here. Do not plug anything in yet until you take the derivative with respect to time. Okay, so taking the derivative, both sides of the equation, we get dv dt is equal to the derivative of everything on the right side. So we get that dv dt is equal to 4/3. Derivative of r cubed is bring the 3 to the front times pi. Pi is just a constant, so it multiplies the 3 there. R squared, and then chain rule says to multiply by the derivative of r with respect to time. 3's cancel out, and we get dv dt is equal to 4 pi radius squared times the rate of change of r with respect to time, but now radius is 9 here, so we're gonna do 2 different radii. First we'll do when r is equal to 9, so we plug in 9 for r here, square, and then dr dt is also given here. Remember, that's 3 inches per minute. Now let me add the units here to the quantities, to our values, so that you know exactly what units to get at the end here. Now before we evaluate this product, go ahead and do the same procedure for when r is equal to 36. Everything's the same. We just plug in 36 for r instead of 9. So we're gonna get this similar setup. Now once we put these numbers in the calculator, we get our approximations here. Now for the next part of this problem, it wants us to explain why the rate of change of the volume of the sphere is not constant, even though dr dt, or the rate of change for the radius, is constant. So notice how from the answer in part A, we have 2 different rates here. When r is equal to 9, it's 1 rate for volume, and when r is equal to 36, it's different. And the reason is because even though dr dt is constant, dv dt, the rate of change or volume, is proportional to r squared. If you look at a equation here, after we took the derivative, dv dt is proportional to r squared, not r. So therefore, it's not going to be constant. All right, guys, here's another example where we have a sand and gravel plant. Sand is falling off of conveyor and onto a conical pile at a rate of 10 cubic feet per minute. The diameter of the base of the cone is approximately 3 times the altitude. At what rate is the height of the pile changing when the pile is 15 feet high? So here we have our cone, and the altitude, we're labeling it as h, radius is r, and we want to create a proportion first of something that is being given here by the problem. So we know the diameter is equal to 2 times the radius. Since the problem is telling you the diameter of the base of the cone is approximately 3 times the altitude, we can set up a nice proportion here where 2r, which is the diameter, is equal to 3 times the altitude. In this case for us is h. Solving for r here, we get r equal to 3h over 2, and we'll see how we're going to use this into our equation here. So we know that the volume of a cone is equal to 1/3 pi r squared times h, which is our altitude. And before we take the derivative with respect to time, we're going to substitute what r is equal to from our proportion here. And the reason we do this is that instead of having 3 variables, namely v for volume, r for radius, h for altitude, we're only going to have 2. So we're reducing our 3 variables to 2, because if we differentiate with respect to time, having r in there, we're going to have a dr dt because of chain rule, and we don't have the RDT. We don't have the rate of change for radius. So we need to simplify our problem a little bit before we take the derivative. And that's why this proportion is important, and we needed that from the problem. Simplifying this a little bit, we end up with a volume is equal to 3/4 pi, again, something simplified, times the altitude cubed. Now, so notice how we have an equation in terms of v and h. Now we can take the derivative with respect to time, and we're going to get dv dt is equal to 3/4 times pi, it's just a constant, and then derivative of h cubed is going to be power rule. Bring the 3 to the front, we have h squared times chain rules is to multiply by the derivative of h, which would be dh dt. All right, simplifying a little bit, we get this is equal to 9/4 pi h squared dh dt. Now we're ready to substitute our values, and we have dv dt is equal to 9/4 pi times altitude is 15 feet. We're just going to square that, and dh dt is what we're trying to find. So we don't know dh dt, we're going to solve for that. And what we do know is dv dt is given by the problem. That's the rate of the volume with respect to time, rate of change, and that is 10 cubic feet per minute. Now solving for dh dt, we're going to get, moving everything else to the other side. That's how the feet squared cancels out, leaving us with just feet over minutes. And we simplify it into 40 over 9 times 225 feet per minute. And of course you can put this in the calculator and get an approximation. Don't forget the pi in the denominator. And we're just going to leave it in the exact form, simplify as 8 over 405 pi feet per minute. Okay, here's one more example where we have a ladder 25 feet long. It's leaning against the wall of a house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. So I already have a picture here for what's going on, and notice how the ladder here forms a right triangle with the ground and the building and the house in this case, and where the length of the ladder is the hypotenuse. Okay, now if we pretend the ladder is being pulled away from the building, from the house, at the rate of 2 feet per second, that's where that arrow indicates there. We want to figure out the rate of change, or how fast the ladder is moving down the wall when the base is 7 feet, 15 feet, 24 feet. So this is the first question. We're going to have a few questions to answer from the same problem. The first thing we want to do is label our sides here. Since these two sides in the right triangle are going to be changing, we're going to call them x for, if we have this angle here, theta as a reference. Opposite to theta, we're going to have x, and adjacent to theta, we're going to have y. Now notice how as x increases, since the ladder is going to be pulled away from the house, y decreases, right? And this 2 feet per second happens to be now dx dt. Since I'm calling this side x, that's the rate at which this side is going to be changing. And dy dt is the rate of change for the other side, and we don't know that. That's what we want to find for part A. Now we need to come up with an equation that puts all of these quantities, all of these variables together, and there's nothing better than our Pythagorean theorem here to put x and y together in one equation. And we know that x squared plus y squared is equal to 25 squared, and we now are ready to differentiate implicitly with respect to time. Now think of x and y as functions of time, functions of t. So that when we take the derivative, you apply chain rule here. Derivative of 2x is derivative of x squared is 2x times dx dt. And similarly for y squared, the derivative is 2y times dy dt. Now 25 squared is just a constant, so the derivative of a constant is just 0. From here we're ready to substitute our values. But first we're going to solve for dy dt, since that's the quantity that we want to find. Moving everything else to the other side, we get that dy dt is equal to negative 2x dx dt divided by 2y. 2's cancel out, leaving us with dy dt equal to negative x over y times dx dt. Now, what is x and what is y for us here? So in the problem, they want us to find this dy dt for different x's. They're giving us x when the base is 7 feet, 15 feet, and 24 feet. So we're going to start with 7 feet here. When the ladder, or this base here, this x, the length here of the horizontal length, x is equal to 7, then we can use our Pythagorean theorem to find y, plug it in, and then we get that y is going to be equal to, and you can just solve for y here and get 24. So then dy dt is going to be negative 7 over 24 times dx dt, but dx dt was given in the problem as 2 feet per second. So plug that in, and of course you can just calculate, and we're going to leave it as a simplified fraction here. This will be equal to negative 7 over 12 feet per second. Now in the same way, when x is equal to 15 feet, and we're going to figure out what y is. From our Pythagorean theorem, we get that y is equal to 20. Okay, so then that means the dy dt is going to be equal to negative 15 over 20 times dx dt, which is still 2 feet per second. We get negative 3/2 feet per second. And notice how all of these results are negative, and the negative here represents that is decreasing. This length is decreasing. That should make sense, because as we said that as x increases, right, y is going to be decreasing because that ladder is being pulled away from the house. Okay, in the same way, we're going to find dy dt for when x is 24 feet, and we follow the same procedure here. Okay, when x is 24, y is equal to 7, and then with that we can plug it into our equation for dy dt. Okay, once we do that, we get a negative 48 over 7 feet per second. Okay, for the next part, we want to find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. Here we know area of a triangle is 1/2 times base times height, and because we have a right triangle, the base is exactly the x and height is y. Right, so then we have our formula here so that we can differentiate now with respect to t. Now remember, x and y are functions of t, right? They're changing here with time. So then when you take the derivative here, you're going to get dA dt is equal to x times y. They're both functions of time, so this is a product. We're going to have to use product rule, and then don't forget about chain rule as well. So since they're both functions of time, we're going to have to apply chain rule here. So then we do your product rules. Derivative of the first one be 1/2 dx dt times the second one plus the first one, 1/2 x, times the second one. Sorry, times the derivative of the second one, dy dt. After we differentiate, we can start plugging in our values here. And remember, this is for when x is equal to 7. Right, so then dA dt is equal to 1/2. dx dt, remember, was given by the problem. That's 2 feet per second. And then y, when x is 7, we did this on part A, y is 24. And then plus 1/2 x is 7. And then dy dt we figured out in part A as well. So that would be negative 7 over 12 feet per second. Cleaning this up a little bit, we get dA dt is equal to 24 feet squared per second minus 49 over 24 feet squared per second. Okay, putting those two together, we get 527 over 24 feet squared per second. All right, for The last part here, the problem, we want to find the rate at which the angle between the ladder and the wall of the house is changing. Okay, when the base of the ladder is 7 again, 7 feet from the wall. Okay, for that, in our diagram, we had a theta already drawn, and that's the angle we're referring to, right? The angle between the house and the ladder. We want to find the rate at which that angle is changing. So for that, we're going to use one of our trigonometric functions, and we can just use sine here. Sine of theta is equal to x over 25. You do not want to plug in the x or the 7 here for x until you've taken the derivative. You never want to plug in your values, substitute your values, before you have taken the derivative. Once we've taken the derivative, we can substitute all the values that we have, all our quantities. So derivative of sine theta is going to be equal to the derivative of the right side here, x over 25. Derivative of sine is cosine of theta, and remember theta is a function of time, so then chain rule says to multiply by d theta dt. All of that equal to derivative of x over 25. 1 over 25 is just a constant. Derivative of x is just 1, but chain rule says to multiply by dx dt. All right, guys, so the only thing we still need to figure out is what cosine of theta is, because we know dx dt, that's given by the problem, and d theta dt is what we're trying to find. So cosine of theta is not given, but we can figure it out by just looking at our right triangle. Cosine is equal to y over 25, and since y is 24, when x is 7, y is 24, cosine of theta is going to be equal to 24 over 25 times d theta dt equal to 1 over 25, and dx dt is equal to 2. We simplify, 25's cancel out, solve for d theta dt, moving the 24 to the other side, we get 2 over 24, so d theta dt is equal to 1 over 12 radians per second.